Um, all right, so look, first thing to say is if anyone is being observant out there, then you'll notice that the title on this slide is not the one that I submitted for this talk. So the title that I submitted was taken directly from a recent paper. It's in JGR Oceans. So the lead author of that paper is my PhD student Noah Day, who was mentioned earlier by Alex. And I'm presenting his slides without any change at all. I noticed that Noah is in the audience. I hope that he's only got half an eye on this talk, and his main attention is on writing up his thesis. These slides were taken from earlier in the year. You can see a date in the bottom right-hand corner there, and also who it was presented to. But it was in a point during the process which the paper was under review. And we had a bit of a snappier title at that stage. That we had two really good reviewers for the paper, and they kept us very honest, in particular about the title. But it got a lot longer, but as a result of that. Okay, so look, the motivation for this work, I guess for me, comes from a bit of a realization a few years ago, in particular when we were pulling together the Phil Trans special issue on the marginal ice zone. Now I'm as guilty as anyone else of this, but what I see a lot is that people in this community will write something at the beginning of their papers as motivation along the lines of, the marginal ice zone is highly dynamic, has all of these properties. And then they'll just move on and investigate their favorite attenuation model or something like that. And there's never really anything to back those statements about the different properties of the marginal ice zone in relation to the interior ice pack. So I wanted to look into that. And that means that we need to define the marginal ice zone. And I'm sort of seeing into the future in the questions here that it's all going to be about how the marginal ice zone should be defined, because it's a topic that this community loves talking about. Anyway, let's see. But I'm going to present you with something a little bit different to what's been done previously. I'd be interested to know what you make of it. And it all leverages on the new flow size distribution capability that's been built into the SICE numerical sea ice model. It's a really important step forward for the field that's been done. I'm really happy that Leslie Rose, Cecilia Bitts, and so on did that. It is not perfect at this point in time, and it needs further development. And it's great to get as many people from the community working with that model so that we can push it forward. So look, the context for the stuff that I'm going to present is that we'll be running the SICE model in standalone mode. That means that there are going to be no feedbacks to waves, to the ocean, to the atmosphere. And the result of that is that the ice cover predictions are far from perfect. Hold my hands up about that. But I just want to emphasize that the results that I'll present are really comparing the properties of the marginal ice zone to the interior ice cover. And so I think those relative measures should be valid. Okay, look, that was a rather long rambling introduction, but to compensate for that, I think for this audience, I can skip over the motivation. You should all be very motivated to study the marginal ice zone and to have a good idea of what's involved in particular interactions between waves and the sea ice cover. And yeah, I think I'll skip over this part of the motivation as well and get straight into it. So our first job is to identify the marginal ice zone. There's already been some discussion of the ways of doing this in the Zoom talks that we've had. In particular, Alex Fraser's talk at the beginning of the day. At this point, I hope that no one in the audience has any belief in the sea ice concentration definition. If you do, then shame on you for that. So there's also the wave definition, which was the basis of Alex's talk earlier. Now, I think that is a much better definition than the sea ice concentration one. I often know criticism of it at all, but I'll only make the comment, let's say, that there's some amount of uncertainty about it if you have these instantaneous views of where the waves are in the ice cover, because you could have a part of the ocean which should be defined as being part of the marginal ice zone, even if waves are not there at a particular instant in time. The definition that I won't exactly go with, but I'm far more aligned to, is the one that I guess was promoted by Danny Dumont in particular some years ago now, of using flow sizes to define the marginal ice zone. So here's the setup of our model. We're using size 6, and as I alluded to at the beginning, we're interested in using that because it has a flow size distribution. And so what it has in comparison to most other numerical sea ice models is what we call an FSTD, flow size thickness distribution, as opposed to just an ice thickness distribution. I already mentioned that we're running it in as a standalone model. It's been run at a 1 degree spatial resolution. So as a result of that, the grid cells around the marginal ice zone are sort of between 50 or 60 kilometers. I mean, it's not ideal. I hope the results that I'll show you convince you that there's some validity to these 1 degree results. But what you have to realize is that either we're defining a cell as being part of the marginal ice zone or not. So it's 0 or 50 to 60 kilometers in terms of the marginal ice zone width, where we're the resolution that we're working with here. Now, in order to activate all the features of the flow size distribution within size 6, we have to put waves in there. So we put what we call a waves in ice module into size 6. It is a pretty straightforward module. It has the 2 key elements that we have, wave attenuation, and we've just used the empirical attenuation that comes from that Bennetts et al. Paper in 2014 that's already been mentioned in this meeting. And then that activates the ice breakup within size 6. It's just a 1-dimensional model. We just run along constant longitude, so we're going directly south in terms of the waves. It's forced by WaveWatch 3 data, so we pick up some mean wave properties close to the ice edge, and then we feed those into the wave in ice module, and then the attenuation takes over from there. We run the model for 10 years, 2010 to 2019, and then we take all of the data for the sea ice in the Southern Ocean and analyze that. Now, our approach to identifying the marginal ice zone is to divide the Antarctic sea ice into different regions, and we do that based on snapshots of the ice cover. Uh, we take 5 variables in order to do that, 5 variables for the sea ice. So those are the sea ice concentration, the ice thickness, the ice age, flow size, and the snow thickness. Um, we, we made the decision about those 5 variables long enough ago that I can't remember exactly why we decided on them. We definitely did some experiments. What I do remember very clearly is that flow size is the most important variable to include. If you don't include flow size, then you get something very, very different to what I'll be showing you. But if you only use flow size, you get different results to the ones that I'll present. And I would argue that the results that you get from flow size alone are inferior to the ones where you include these other variables. So then we take all of our data over the 10 years for the Antarctic sea ice, and we apply something called k-means clustering to it. So this was all Noah's idea. I had no idea what k-means clustering was before this, although it has been used for sea ice data previously, just not in the same way that we're doing. So essentially the idea is that you take this large amount of data and then you divide it into distinct clusters. So we've got a simple example on the right-hand side here where we're just considering 2 variables. And this is Noah's idea, Noah's way of showing you what's going on. So you have to prescribe to the k-means algorithm the number k of clusters that you want. We've chosen 2 here. And then based on some centroids that the algorithm identifies and the distance of the data points from those centroids, it will separate the data into different clusters. I mean, technically, this is some sort of machine learning, which I swore I was never going to use in my research. But then Noah has switched the light on for me, and I'm fully on the bandwagon here. So the first question that we have to answer, the main question, is how many clusters are we going to use? What I'm showing you here are some example results where we chose either k is equal to 2, 3, or 4 clusters. So going from left to right. And these just at the sea ice maxima in some year. Now, we've identified the clusters on the maps at the top with different colors. We've colored the one at the outskirts of the ice cover in red, and that is the cluster that we want to represent the marginal ice zone. So what you can see is that as we increase the number of clusters, the red band becomes narrower. We came up with an argument that 3 clusters is the best, and we did that based on an argument about the waves. We took the waves at the inner boundary of the red cluster, and we decided that what we wanted in order for that cluster to best represent the marginal ice zone is that occasionally we would get non-negligible waves reaching through to the interior of the marginal ice zone into the inner pack ice. And so the evidence that k is equal to 3 is best is represented by those histograms at the bottom. So the bottom left, you're seeing that we're not very often, we chose a significant wave height of 1 meter to be non-negligible. So only 0.1% of the time are we getting waves greater than 1 meter through to the interior of the ice pack when we have k is equal to 2 clusters. If we have k is equal to 4, then a third of the time we're getting waves of that size getting through. But if we choose 3, then it's just over 10%, which we thought was quite reasonable. So that's our argument for k is equal to 3, and from now on I'm going to stick with 3 clusters. So what you're seeing here are on the top right are some snapshots at different times during the year showing you the 3 clusters. At the bottom right, we have the seasonality of the areas covered by those clusters. Probably the most interesting, or definitely the most interesting for the sake of this talk, is the behavior of the seasonal behavior of the area of the outer cluster, the red one, which we're now going to call the marginal ice zone. So what we can see is that there are 2 peaks during the year. There's a winter peak here, and that comes from the new ice forming, and that new ice is put into the marginal ice zone cluster by the K-means algorithm. There's another peak, a slightly smaller one, that occurs during the summer. And that comes when the ice gets weaker and the waves are able to break up the ice cover into smaller flows. Because as I'm stating out on the left-hand side here, a general description of the ice cover in that cluster that we're associating to it is that the ice there is smaller, so the flow sizes are smaller, it's younger and thinner as compared to the 2 interior clusters. Okay, so I've got one more set of results which are comparing the sort of ice covers that we get with 3 different clusters. The plot on the left-hand side, well, what can I say about this one? I remember Vernon Squire telling me when I was earlier on my postdoc with him that every good paper needs one figure that nobody understands, and I think for us this is the figure. So maybe concentrate on what's going on the right-hand side. So here we're comparing the probability distributions of the ice cover in the 3 different clusters. On the top, we've got the flow sizes. In the middle, we've got the sea ice concentration. And on the bottom, we've got the ice thickness. So what comes out very clearly here is that in the marginal ice zone cluster, the flow sizes are smaller because they're peaking towards the smaller flow sizes here. And they're also thinner. You can see that the peak is distinctly lower in terms of thickness as opposed to the 2 other clusters. The concentration is less clear. Again, you get what you would expect, that generally in the marginal ice zone, the concentration is lower, but the distinction is far less pronounced than it is for those 2 other variables. Now, these are probably the standout results. I mean, I remember very clearly when Noah brought these results to me, and then this will really maybe sit up and take notice of this approach to defining the marginal ice zone. So what you're seeing in red here is the predictions of the marginal ice zone effective widths over the year. So this is averaged over the 10 years. And effective means that we're also taking the concentration of the ice cover into account. And the reason that we chose to do that is so that we could directly compare with the satellite observations from the paper by Jill Brower, Alex Fraser, et al. So those observations are shown by the green markers and error bars here. So they are observations of wave penetration distances into the marginal ice. So it's an entirely different way of thinking about the width of the marginal ice zone. But the agreement is really remarkable. I mean, I know there are a few differences, but I mean, they're just looking at particular regions and much smaller data sets, and I think just over 1 year. It's really incredible that the measures are so close of the effective marginal ice zone widths here. In particular, the shapes over the year of marginal ice zone widths really stand out, the agreement there. In grey, you get the predictions of the marginal ice zone width coming from the sea ice concentration definition. And probably as you'd expect, the shape is completely different. In particular, the marginal ice zone width is basically 0 during winter if you use that sea ice concentration definition. Although, before I trash that any further, I should point out that part of the reason it's 0 is because we're running the sea ice model in standalone, which gives too high concentrations at the outskirts of the ice cover. So that's partially to blame here. So now we're just going to focus in on some of the properties of the marginal ice zone that are predicted by the standalone model. What you can see at the top here is the marginal ice zone width. It's just the straight width now, not the effective one. Then we have the sea ice concentration, the flow size, and the ice age. So the highlights are out here on the left-hand side, dividing between the winter and the summer. So in the winter, we have high concentrations where the new ice, which you can take to be pancake ice, is forming with the frazzle ice between. And that means that the ice cover is young as well. Then in the summer, we have melts and the concentrations get lower. All of that pancake ice is either consolidated or has melted away, and then the marginal ice zone is being formed by wave-induced breakup of the ice cover, and that results in larger flows. And it's ice that survived from the winter into the summer, so it's relatively old. And here we're looking at some of the dynamic properties of the ice cover. And we're comparing the properties in the marginal ice zone to the properties of the interior ice cover. So the interior ice cover is now what I was calling earlier clusters 2 and 3. We've just combined those two together. So at the top, we are looking at the wave-induced breakup, and unsurprisingly, it's much greater in the marginal ice zone. The one thing that I should point out here is that if breakup occurs in the interior ice pack, and that breakup causes the ice in a particular cell to move from being part of the interior ice pack to being the marginal ice zone, then it's counted here as being part of the marginal ice zone. Otherwise, you would get far closer results in terms of the breakup. And the other thing, which is just confirming what we'd expect, is there's basically no breakup that is occurring during the winter. It's all occurring during the summer months. In the middle, we have the ice speeds, and we can see that the ice speed in the marginal ice zone is always greater than in the interior ice cover, and that particularly occurs during this phase of the year, sort of towards the end of winter and the beginning of summer. And then we have the melt rate at the bottom. Again, it's much greater in the marginal ice zone than in the interior ice cover, and as you'd expect, particularly during the summer. And now we're just going to get into a little more detail about the dynamics and the thermodynamics and the drivers of those differences between the marginal ice zone and the interior ice cover, starting with the melt rates. So at the top here, we have the total melt rates. The thin lines that you can see are the data that come from each individual year, and then we have some moving average. There's the solid line that goes between them. So that's basically what we saw on the previous slide. Now we've divided into the lateral melt in the middle here and the basal melt at the bottom. So two things to note. Firstly, that the y-axes are different between the basal melt and the lateral melt. So the basal melt goes to higher values because you get more melt coming from the base than you do from the edges of the flows. But for the basal melt, although the marginal ice zone is greater than the interior ice cover, it's only by a factor of up to about 2. Whereas for the lateral melt, the difference is far greater. So that fairly obviously is coming from the fact that we have smaller flows in the marginal ice zone. So that is increasing the lateral melt. Oh, and in case it's not completely obvious, the increased basal melt is simply coming from the fact that the marginal ice zone is farther north than the interior ice cover. So the ocean temperatures are greater there.
Luke,
And
just sorry to jump in here. Just a few minutes left.
oh, thanks, Mike. Okay, yeah, I'm basically done. Um, so now, in terms of the ice drift, this is what you saw a couple of slides ago. Now, what was known is that the drift speeds are highly correlated to wind speeds, and part of this difference is coming from higher wind speeds where the marginal ice zone is. But what we're highlighting here is that the model is predicting that the difference is also coming from a decrease in the internal stresses or the rheology in the marginal ice zone versus the interior ice cover. And that in the model is coming from thinner ice in the marginal ice zone and also lower concentrations in the marginal ice zone because there's no flow size dependence in the rheology in the model at the moment. Okay, so this is just confirming about the relationships between the drift speeds and the winds. I think in terms of time, I'll just skip over this. I'll skip over this as well. Now, I just wanted to say something a bit provocative at the end here. Alex showed us comparison of his satellite measurements with our model earlier and showed us how good it is. I'm just emphasizing that here. And I want to make the point again that the wave and ice module that we've got here is incredibly simple, yet we are getting very good agreements with these satellite observations. So I think I might not actually believe this statement, but I think it's a good discussion to have about how much sophistication is needed in terms of the wave and ice models depending on what outcome you want from the overall model. This is indicating that perhaps something very simple is going to do an effective job. Okay, and here are the conclusions. I've run out of time, so maybe I can just take a question or two to finish with.
I mean, thank you, Luke, for the great talk. And there's plenty of time for questions because, you're the last speaker. Unfortunately,